All right, so I'm not going to be here on Thursday, so we are going to do both parts of the E notes today. They're both pretty short and they go together, so it's really not too strange. And Joe figured it out. He figured it out. Okay. So 22E is all about compound events. As you can see, 22E1 is independent events. E2 will be dependent events, and so I'll be explaining the differences between independent and dependent. What do you guys think about when you see the word compound? I always think of the same thing, but I'm curious what you guys think about. Combined. Me too. I always think of compound words where you combine two words together to make one word. So compound events are we are going to take two events and put them together into like one event. If you have not already drawn your stop box, go ahead and do that. So here are compound events. They're when two separate events happen and we consider their outcomes together. Even like if you are playing I know there's some board games we have to roll two die at once, right? So like each die is a separate event. But if we want to roll, two twos or something like that, then we have to combine that together into one event. Like what's the probability of rolling two twos? Or snake eyes, 2 1. So they're separate events, each die, but we think about the outcomes together. So if we just think about this for a second, what is the probability of flipping a coin flipping a coin, getting ahead, and then rolling a die and getting a 3? So these are two separate events. I feel like something was missed in these notes. This is weirding me out right here. Nope, just kidding. I'm overreacting. All right. Okay, so they're two separate things, right? So what's the probability of getting ahead? 1/2. Yeah. I thought you said 1/2, and I was like, yeah. All right. And then what's the probability of rolling a 3 on like just a normal 1/6? So you're gonna have this in a formula on the next slide here. But what we do is these are two separate things. And we end up just multiplying them to get the probability of them both happening. So that'd be 1/12. But just to kind of get you guys thinking about how that probability works. And again, this is on the next slide. So the thing is about those events that we were just talking about, they're independent. The outcome of one does not affect the outcome of the other. This is another typo thing I meant to fix, but didn't. So the outcome of one does not affect the outcome of the other. So flipping a coin and getting ahead does not impact what number I roll on the die. They're independent. They don't affect each other as far as what would happen. So then, to determine the probability of a compound event made up of two independent events, just multiply the probability of the two events. So that's what I was saying. So again, if A and B are independent events, that the probability that A and B happen is equal to the probability of A times the probability of B. And then underneath it just goes to say that you've got 3 events, then you multiply all 3 things. So it works the same way. Is everyone ready? Let's try to watch the hand. So we're going to do a few examples here. This first one is a coin is tossed 4 times. Determine the probability of getting the following sequences of results. So we're flipping a coin 4 times. And again, these events are independent because the first coin flip doesn't change what the second coin flip will be. Like, they're independent. They don't have anything to do with each other. So the first situation is that what is the probability we get a tail and a tail and then a tail and then a tail? Well, what's the probability of getting tails the first time? And the second time? The third and the fourth? Still 1/2. So we just have to multiply all of these together in order to get our probability. And I didn't explain this or remind you guys out loud when we did this on a different example, but remember when we multiply our fractions, we multiply the numerators. So I get 1, and then 2 times 2 times 2 times 2 is 16. Are there any questions about that? What do you think the probability is we get a heads and a tails and a heads and a tails? Yeah, it's the same because it's still 1/2 for each of those. So I don't think we really need to show our work on that one. We're going to do one more example. It's got a few parts to it, but one more example that's set up a little bit differently before we switch to dependent events. Do you guys remember doing this before? Probably in like middle school or maybe freshman year? Yeah? Okay, I'm hoping that it's not like 100% new, but it's been a while so that the refresher is like nice. So here is our next example. 2 soccer players take a shot at a goal simultaneously. Joe makes a goal 60% of the time, and Lori makes a goal 80% of the time. Determine the probability that, we're actually going to do 4 different questions, 2 on this slide, 2 on the next, that have to do with this example. Again, these events are independent because Lori making a lot of goals doesn't really affect how many goals that Joe makes. Like, they're not related to each other. So what we have to do then is turn these into fractions. So if Joe makes a goal 60% of the time, that means 60 out of 100 shots he makes. So you can either reduce it now or reduce it at the end. I don't really care. For some reason, I was reducing at the end, but it does not matter. What do you guys want to do? You want to simplify and reduce this fraction now, or you want to do it later? Now? Okay. So then, if I reduce it, it's going to be 3/5. So, Joe makes the goal 3 out of 5 times. We can do the same thing with Lori. Her percentage is a bit better. She makes it 80% of the time, which would be 4/5. She makes 4 out of 5 shots. So the probability they both make a goal, well, Joe is 3/5 and Lori is 4/5, and we just multiply them. 12/25 or 0.48, depending on if you enjoy the decimal versus the fraction. It's your call. Just, be able to interpret or understand both. Other questions on that one? So what about missing a goal? So if Joel makes 3 out of 5 goals, how many does he miss? 2 out of 5. Okay, 2 out of 5. So then if Lori makes 4 out of 5, how many does she miss? 1. Do those numbers make sense to you guys? Okay, so then we would use those. So Joe missing the goal is 2 out of 5. Lori is 1 out of 5. So I get 2 out of 25, or I think it's 0.08. I know this probability stuff is not too crazy, but again, since it's been years, we gotta have this review. The next two, again, related to this example, I'm going to have you guys calculate on your own to get a little experience with calculating that probability with independent events. But is there any questions or concerns? Okay. So I'm going to give you guys a few minutes to calculate these two. Probability that Joe makes a goal and Lori misses, and the probability that Lori makes a goal and Joe misses. Could be practice there either end. Especially since we're doing independent, we're not factoring in maybe Lori's call deflected shows we're not going there right now. Okay. How many of you guys got the first one? Joe makes it, but Lori misses. You got it? Miranda, what'd you get? Yeah, 3/25 or 0.12. Now, if you're not getting that calculation, let me know so I can check out your notes or your calculator, see what's going on. What about Joe missing, but Lori makes it? All right, 8/25 or 0.32. After the stat box, we are going to switch to the E.2 notes. So, are there concerns about independent events? So I would just, in your stat box, maybe leave room so that you can do both stat boxes for both notes in the same stat box. But explain in your own words what an independent event is, just something so that you will, remember it. The next stat box is going to be like, well, what's the difference between independent and dependent? So if you want to leave yourself a little space for that, that's good too. So the homework for E.1 is all. So make sure you write that down, because I am going to have to switch the screen so that I can get to the other set of notes. So when we talk about compound events, we have to talk about the independent events, but then we also have to talk about the dependent events. So that's what the other half of this section is about. Like I said, I don't think you need to draw another stat box. But here's what dependent events are. The outcome of one event actually changes the likelihood of the other event. So they do affect one another. So if we go back to my starburst example from when we talked about sample spaces, if I take out one starburst and it's pink, that changes how many pink starbursts are still in the bag. That also changes how many total starbursts are in the bag, so it actually changes the probability that I get that second starburst. So the second event depends on what happens in the first event. The phrase without placement means that once something is removed from the pool, it's gone. So once I take out that pink starburst without putting it back, without replacement, it changes, like I said, how many are in there still. That phrase without placement is a very big key of this is dependent. This means that things are changing. The second probability depends on what's happening in the first one. So that's like your clue that they're not independent. So we're just going to hit 2 examples of these types of events, and then we'll call it quits for notes today. So here's the first example. There's a box with 5 red and 3 blue pens. So you draw 2 pens sequentially from the box without replacement. So you take 2 pens, you're not looking. The question is, what's the probability that both of those pens are red? This is dependent because once I take 1 pen, the number of pens still in the box changes. Once I take 1 red pen, the number of red pens in the box changes. So it changes that probability. It affects the probability of the second piece to this. We still do the multiplying because it's still a compound event. So I find the first probability, multiply it by the second probability. But it's just a little bit more thinking to get that second probability. So what's the total number of pens in my box here? So the total pens is 8, so that's that sample space, because there are 8 different things that could happen, technically, when I pick some pens out. So for my first pick, and then I'll have my second pick. For my first pick, there are definitely 8 pens still in there, and 5 of them are red. So 5 out of those 8 pens are red. Now the thing is I take that pen out. I do not put it back, hence it says without replacement. I don't put that red pen back. I still have it. So how many pens are left in the box? And I took out one red pen, so how many red pens are left? Do pay attention, because like if the question was one red pen and one blue pen, there'd be 3 out of 7 blue pens. You know, I might not have to subtract, so just make sure you are paying careful attention. Once I have this set up, I just multiply straight across as per usual. So I have 20 over 56, which reduces to 5/14 or 0.357. We just have one last example, but are there concerns here about dependent? While you guys try this one on your own, it says consider a lottery drawing with cards numbered 1 through 20. If we draw out 3 cards sequentially without replacement, what's the probability that all 3 are even numbers? So again, give this a shot. Let's see how you do with it. How are we doing? So there's 20 cards total, 1 through 20. So I start out with 20. Seeing mostly good answers when I walk around. How many of them are even? 10, half of them. And if that doesn't come to you like intuitively, I mean you could be like 2, 4, 6, 8, like that's fine. So I take out one card. So now there's no longer 20 in there, there are only 19 cards. And I took out an even, so there's no longer 10 evens, there'd only be 9. Similarly, for my third pick, I take out another card, so there's only 18. And since I took out another even, there's only 8 left. And then we would multiply all of those. And I suppose you could reduce those. I just feel like I don't know, I just reduce at the end for these. I'm not sure, I don't really have a reason why, I just do. So when we multiply straight across, we get 720 over 6,840. Which is 2/19 or 0.105. Are you guys having any concerns? So if in your stat box, I'm going to go to the screen, but just like what's the difference? Like how are dependent events different than independent? Again, remember that stat box is just to like go back to, you can make sure to that page, you kind of get an important bit of information. how would you explain the difference between independent and dependent events? So whatever is going to make sense to you when you look back to know the difference. Now remember, this is for 22E.2. I'll just write 22E.1 just in case someone was zoning out. Yeah. So I already said I did both sections so that you guys can work on these tomorrow. Also, I told you guys there was going to be a quiz this week. Joe figured it out. It's tomorrow. E won't be on the quiz, okay? So obviously you just got E today. You won't have time to ask questions on it, so E is not going to be on the quiz. But be ready with all those other sections. There's still a solid 15 minutes left, so if you have